Okay, so back in Math 30, you learned the binomial theorem, okay, and we've talked about that already in the last unit. And so that's for expanding a binomial. Then we looked at the similarities between that and binomial probability distribution. So you use the binomial probability if it either happens or it doesn't happen. So basically two probabilities. One that it happens, sometimes we call it a hit, and the converse of that is a miss, or the complement of that. So we can find the probability of certain things happening, if it can happen or if it can't. Not if you have other options in there, or a variety of different probabilities. Okay, so this is the formula for it. Okay, notice how in IB I put the n up here. You may have done the n below. We talked about that in the last unit. Probability of the event happening multiplied by the, this is the probability that it doesn't happen. Okay, and so x would be the number of hits, successes, and that's the probability of that. Then obviously the probability of misses or unsuccessful events will be the difference between the total events in it. It's not in the data booklet, so from what I can tell, anytime you're asked this on your IB exam, it will be on a calculator portion of your exam, so you can use your calculator. Okay, so remember in your calculator, it has binom PDF and binom CDF. This is what we use for exact number of hits or successes, and this is cumulative. Okay, so that's for a range of hits, 0 to 5 hits, so maximum of 5 hits or something like that. So that just explains that there. Newer calculators, actually, I think, I got a better calculator on this replacement computer, but we'll have to look because you don't even have to think even as much as you used to in terms of what to enter for a cumulative anymore. So we'll talk about that as we go through some examples. So when a random variable follows a binomial distribution, this is the notation that you'll see. So there's your random variable x. They use capital B for binomial distribution. N is the total number of possible events. P is the probability of a success. So let's do some calculations. So a fair coin is to be tossed 100 times. Determine the probability that heads will occur. And I spelled that wrong. It's just one R. 65 times. So that is exactly 65. Okay, so that's going to be a binom PDF. So binom PDF. And even though IB doesn't really like calculator notation very much, like certainly on an exploration, but they're not giving you the formula, okay? They're going to say calculate to a certain decimal, well, actually, it could be 3 significant digits. It's not going to be worth a huge number of marks, but you need to put down what you're entering in your calculator, right? So, or write it out. So here, this would be n, right? So n equals 120. Here, probability of a head is 1/2. Okay, and the number of successes, so you can call it x, is 65. So way to write it out, this really comes from the older version of the calculators, is 120, 1/2, 65. So here, let's see if I have to press this twice now. So distributions, so second vars, I'm going to do second vars. There'll be cursor up to binomial PDF. Okay? Newer versions will prompt you. Older versions, you have to write it in, okay, or punch it in with commas in between. So here, trials are 120. I had just tried this one, make sure this calculator worked. Probability is 1/2, x value is 65. So most of your calculators look like that, something similar. Okay, so in this one anyway, it says paste. Sometimes it'll just say calculate. Paste, it actually puts it into that form there. Okay, and then enter on that. So we'll go 0.0481. Okay, so that doesn't count as a digit. We'll do 3 digits afterwards. Okay. All right, the next one. Each time a soccer player kicks the ball, she has a 75% chance of scoring a goal. If in a particular game she kicks the ball 12 times, determine the probability that she gets goals in at least 10 of those 12 kicks. Okay, so here, what do we have? So we have n equals 12. The probability of scoring a goal is 0.75. And then here, x is in at least. So x is greater than or equal to 10, less than or equal to 12. Right? So it could be 10, 11, 12 kicks. Okay, that she gets a goal. So this would be binom CDF. You can do binom PDF 3 times, right, and add them together. You can even do that in a sequence or sum, but I would use CDF. Okay, so in your your number of trials is 12. Your probability is 0.75. Now we got to, in the older version, we had to do a couple things, but newer versions, I think you got it pretty easy here. So let's just check it out. So second vars CDF. Okay. Now, do you guys, when you do that, have like a left and a right? Can you show me? Upper and lower. Okay. Who else has an upper and lower? Oh, you're the only one?
I have that too, but my calculator.
Yeah, no, I thought some of the newer versions had, just of the 84s had that. Can you show me what? Yeah, okay. So, what we have to do here, so basically, you can do it, you guys, by upper and lower. In this case, total probability of a distribution is 1. We want everything, everything between 10 and 12. When you do CDF, it goes up to the value that you enter here for x. So this is going to be cumulative from 0 up to whatever value you put here. So we don't want 0, right? So if we put 9 here and go total probability minus the probability from 0 to 9, that gives us the probability from 10 to 12. Okay, so that's how you get around that in the kind of the fastest way. So here, I'm going to number of trials, 12, probability 0.75, x value is 9. Okay, so that's the probability from 0 to 9. So we go 1 minus that. And 0.391. So here, 0.60932. And then we'll round at the end, 0.391. Okay. In terms of what notation, you can call this probability of, it's not x equal, well, I guess you could go x equals here 10, 11, 12. Okay, next one, the probability of a light bulb being defective is 0.03. If there are 100 light bulbs in a case, determine the probability that no more than 2 light bulbs are defective. Okay, so I've got n is 100. Probability of being defective is 0.03. And we want the probability that no more than 2 are defective. So that means we want the probability of 0 defective, 1, and 2. So our x's here are between 0 and 2. Okay. And so that's okay. This is a cumulative, but it's starting at 0. So we don't have to do any 1 minus on this one. So if you want to write this out, that's probably good form, which I did at the end there. But here, 0, 1, 2. So that's going to be binom CDF 100, 0.03. And then you put that maximum value 2. CDF. Now we're doing 100. Three, and then 2, and then, okay, so then rounding to 3 digits, that makes, the 7 makes this goes up, so that's going to be 0.420. All right, so now, mean, expectation or mean, variance and standard deviation of binomial probability distribution. So, remember, a binomial probability distribution is a form of a discrete probability. You can't have like half of a goal, right? Or half of tossing a head. So it is discrete. So we're just going to multiply by probability times the number of occurrences. So a fair 6-sided dice is to be rolled 120 times. I think dice is plural. Die. On how many occasions would you expect the result to be a 6? So you want to know, you want to know the probability of rolling a 6. If it's a fair die, would be 1/6. So this would be the expected value of x equaling 6. And that would be 120 times 1/6. be 20 times. Basically, it's this theoretical, what would happen. May not happen if you roll it 120 times, but it probably will be pretty close to it. But the more rolls you get, then on average it's going to be 20 times. Okay, similar in the next one. Each time a soccer player kicks the ball, she has 75% chance, just like that last one we did. In a particular game, if she kicks the ball 12 times, how many goals do you expect she will get? So that's going to be expected value, where x equals 12 here. And that's going to be, so probability is 0.16. Actually, x is not 12. It's just the probability of that. That's the, yeah, I guess, yeah, that's okay to say this, but we don't know how many. X is the number of goals, right? So just leave it as x, because we're trying to figure out the number of goals that you would get. So x equal, you could put x equals goals, I guess. And here is 12. So it's 12 times 0.75, which would be 9 goals. And then the same one, same thing again in the next one. Probability of being defective is 0.03. N is 100. So the expected value or mean of, in this case, the number of defective light bulbs would be 100 times 0.03. So 3 light bulbs. On average, right? Because that's where the probability came from. If they basically did a huge sample and found that in that huge sample, 0.03 of the sample was, so basically 3% of the sample was defective. So then, to generalize that over 100 light bulbs, is 3% of 100 light bulbs. So that's what we've been doing here. So P is the probability of success, N is the number of trials. Variance. Okay, so for variance of a binomial distribution, we're taking the probability of success times the probability of a failure or a miss times the number of trials. And that's the variance, so so standard deviation is the square root of that. Okay. And I'm pretty sure these, I didn't say they're in the guide. So binomial distribution, expected value NT, variance NP, 1 minus 8. So there you go. Okay, so sometimes you're not even given what the example represents, but you're given this notation, so you know it's a it's a random variable, and it follows a binomial distribution. This is the total number of events. This is the probability. So to determine E of X, it's just equal to 10 times 0.3. And then variance of X is number of trials times the probability times 1 minus the probability. Three times 0.7 is 2.1. Okay. So for that same distribution, it says calculate the probability that X is greater than mean minus standard deviation, and less than the mean plus the standard deviation. Okay, so the mean is the same, remember, as the expected value. All right, so mu minus standard deviation. So mean is 3 minus standard deviation is the square root of 2.1. Okay, then let's do mu plus standard deviation. So 3 plus square root of 2.1. So 3 minus square root 2.1. 3 minus square root of 2.1. Okay, so 1.551. Or just 1.55. So in this case, it's a decimal. If we show this to 3 significant digits, we'll leave it like that. And then 3 plus square root of 2.1. If you have the ability to go back up, you can copy it out. If it will let me go here. Come on. I don't know if that was faster or not, but 4.45. Okay, so we want to find the probability where X is between these.
So is mu like the mean?
Yeah. Mean is the same as expected value for these probability distributions. Yeah, you can put that up here. Okay, so now though, this is a discrete probability distribution. These are decimal values, right? So we want to find the closest value of X that is greater than this. So that would be 2. So really we want to find the probability where X is between 2 and whatever whole number is less than 4.45. So that would be 4. Okay. So then that's going to be cumulative. But remember, unless you have that calculator, the Inspire, you need to think about subtracting values, right? Because it won't, when you put in a cumulative, it starts at 0 and goes up to that value. Okay, so here, we want between these, so greater, so here I should include now equal signs on that. Sorry, I forgot about that. 2 is greater than 1.55, so we can include it. Okay. So that was no equal sign. Now I'm going to put equal sign because that is greater than this. Same with this. You can include equal. All right. So now, basically, if I find the probability from 0 to 4 and subtract the probability from 0 to 1, then I will get the probability from 2 to 4. Okay. The discrete probabilities. So this goes up to 1, so 0 and 1. This is 0, 1, 2, 3, 4. And I want 2, 3, 4. So you can subtract those. Just a little bit. So this would be a case where you don't want to just give the final answer, right? They're going to be wanting to see some marks that you know what you're doing there, right? So make sure you show your mark and work. Just going to do this way faster. Okay, and then second is okay. So 0.8. I always show a few extra decimal places, and then I round at the end, right? 149. And then we go. Oh, sorry. .700. Okay. 3 digits, 3 significant digits. Probably be.
So the 1 standard deviation, like 69%, 70.
In a normal distribution.
Isn't this a normal distribution?
Binomial distribution. Yeah. Yeah, absolutely in a normal distribution it is. Okay, so then try the next one. Similar, we don't know what's representing, but find those probabilities. Okay, again, using your calculator. And then part B is, got to think a little bit about that. Okay, so binom PDF, binom CDF, CDF. Oh, what did I just do? I should post on. Okay, so I'm here using the rounded version because that's all I recorded there, but don't, although it's a 1, so it'll be fine, actually. 1 minus that. Okay, and then this last one here, given that x is less than or equal to 2, determine the probability that x equals 2. That's a conditional probability, right? So really what you're trying to find here is probability that x equals 2, given that x is less than or equal to 2. Okay, remember back. Okay, so then that formula, conditional probability, is in your data booklet, so you can look that up. I think it uses a, actually let's just look at, I always remember it as a in fraction form, but they don't always give it in fraction form. Oh yeah, they do give it in fraction form. So conditional probability is given there. I think it's the Alberta data booklet. They do this in 30-2 and they show it as a multiplication. Okay, so there's your conditional probability. So what you want to do here then, this is what we're trying to find. And then this is going to equal the probability that x equals to intersect x less than or equal to 2 over the probability that x is less than or equal to 2. Okay. Well, if you think about this intersection here is when x equals 2. Right? If you have x equals 2 intersecting with x less than or equal to 2, what intersects? X has to be 2. So that we found in the first one. Okay, so this is going to be 0.302 divided by less than or equal to 2, which is 0.678. Now, in your graphing calculator, you want to use more decimal places than that. So I think most of you have the ability to go up, copy that out, and divide by probability there, enter on that, and then to 3 significance, so 0.446. Now, this one here, actually, because they don't give you the formula, you're just going to use trial and error on your calculator. If you don't, you can actually use algebra from that original formula. for the probability. But in this case, I don't think they're going to ask you, so then choose different values of n. But again, set up your equation. Random variable x is binomial distributed with probability of success 0.6. Determine the least number of trials. So we don't know what n is. We know the probability is 0.6. And we want x to be greater than or equal to 1. Obviously less than or equal to n, right? And that probability is greater than 0.9, okay? So how do we get this? Well, think about it. Probability of x greater than or equal to n. So we'll have here, it's a cumulative probability. We want it greater than. Cumulative always starts at 0. So we want to go 1 minus the binom CDF cumulative. Again, we don't know the number of trials, but we know the probability. And we want to go basically greater than or equal to 1. Oh, actually, greater than or equal to 1. Only thing less than that is 0. So we can just use PDF. Okay, if you use CDF and PDF for that, you should get the same thing for a certain n, because it's starting at 0. Okay, so that has to be greater than 0.9. And then, so isolating this, if we bring this over here, that would be 0.1. And this over here would be binom PDF and 0.60. So we want the value, the least number of trials, so the n value, the smallest that we can get, where the probability of this is 0.1. As I said, you can do it algebraically, but I don't think they're going to ask you. So get out your calculator. And what's kind of nice is it keeps your values. So we could just keep changing here. So we're doing PDF. Trials we don't know. So let's start with 1. And probability 0.6. And x value is 0. Okay, so it's too big. So then if we go binom PDF again, it keeps your values. So now you want to increase your trials. Let's go a little bit bigger. So let's go 4. Well, that is smaller. So maybe I went too high. So then let's go distribution. Let's go 3. Still smaller, so maybe one more try. Because I've done that already. 2. Okay, so 2 was too big. 3 was the first time it was smaller. So that means n is 3. So if when n equals 3, get binom PDF 3 0.60, which is equal to, what was it, equal to 0.064. Okay, 0.064 is less than 0.1 for the least number of trials. Is 3.
That's the last question, right?
All right. So some of that's kind of review from Math 30, and then a little bit extra
Because I'm not sure that we did expectation of binomial distribution invariance back in Math 30. So, and then there's questions in your package. Okay. So tomorrow we'll look at continuous probability distributions. So that means we'll be using some integration to help us, because we'll be continuous functions. Friday's a practice day. Then we'll go back on Monday and Tuesday to look back at some of the probability back from Math 20. Conditional, which we just did one there. Bayes' theorem, which probably we didn't spend much time on. Review on Wednesday. Next Thursday is your last test. So Tuesday is your last lesson. Really, tomorrow is your last new lesson. So there you go. Almost done.